Let's talk about binary numbers. Computers, as you may know, store all information, whether that's code, text, images, sound, anything that's on a computer, as a binary representation. Binary means it has only two parts, and in this case, 0 and 1. But even with just two parts, just those two numbers to work with, there's a lot of information that can be communicated, including specific formats within the binary representation for each file that helps the computer know what type of item or object it is dealing with. Still, why use binary at all? Well, let's think about this. Why do we use decimal numbers? Have you ever thought about that? So our numbering system has ones, tens, hundreds, thousands, etc., each place representing a bigger and bigger growth by 10, which is, of course, what decimal means. So why do we use decimal numbers? Well, you may know that decimal systems are one of the most common numbering systems in languages around the world. And if you think about it, it's kind of logical because we have 10 fingers, right? 10 fingers that we can count with. And actually, one of the other very common numbering systems in languages is the numbering by 20. For example, French, which that also makes sense because you've got 10 fingers and 10 toes, which adds up to 20. So, okay, it's logical then why we would use the decimal numbers. And computers don't have fingers. So what do they use instead? And what do they have? What they have is two states. Their currents can either be on or off. So there's your binary system, and that can on and off can also be zeros and ones. So it really helps when you're working with computers to be able to work with binary numbers and understand binary representation. So let's work through some examples of how the numbering system works. So you probably think that the decimal system is actually a very easy system to use, but that's actually only because you're very used to it. So let's walk through the details of actually what's going on behind the scenes when we use a decimal system. And then you might realize that it's not that much easier to represent numbers in the decimal system any more than it is in the binary system. So how do we represent a number like 50,932? Well, you just heard me say the word, and you can see on the screen there how we represent it. We represent it with those digits. But what's going on here? So we can take those digits and think of each of them being in a certain place. And you learned this in school. You know that each place has 10 digits from 0 to 9. And we use the words ones, tens, hundreds, thousands, and 10,000s, 100,000s, right? And so on and so forth. And that's what we learned in school. What you may not have thought about is that there's another way of representing the value of each of those spaces, which is underneath that chart. So the first space where the 2 is, the ones position, is where you get the 10 to the 0th, which is 1. The next space is 10 to the 1th, which is, or 10 to the 1st, excuse me, here I'm talking in indexing again. 10 to the 1st, which is 10, 10 to the 2nd is 20, 10 to the 3rd, 10 to the 2nd is 100, 10 to the 3rd is 1,000, 10 to the 4th is 10,000. So actually what's going on in the system when we represent with these digits is a lot of math behind the scenes. To represent a 2 and to understand what that means, we're actually doing 2 times 10 to the 0, or 2 times 1, which is 2. To represent the 3 in the tens position, it's 3 times 10 to the 1st, or 3 times 10, which is 30. In the hundreds, 9 times 10 to the 2nd, or 9 times 100, which is 900. And so on. 0 times 10 to the 3rd, or 0 times 1,000, is, of course, 0. And 5 times 10 to the 4th, or 10,000, is 50,000. And that's how we get the value of each of those digits in that order in which they're represented. To get the value and to understand the value of this whole number as it's represented in the decimal system, we then add up our products there. If we add them up, 2 plus 30 plus 900 plus 0 plus 50,000 is 50,932. So that's actually the math that's going on behind the scenes in our decimal system. So it's really not that easy. And we can do the same thing with a binary system. Another way of looking at this representation of the decimal system is to take a little graph like this. So here on the first row, let me get my spotlight. On the top row, we have the number that we want to represent, which in this case is 67,493. Underneath, we can do the representation to remind us of what each number place is worth. And then here's what it is in when not using exponents, the same value. And then below that, here's the value of the multiplication that we just saw in the other one. So 6 times 10 to the 4th is 60,000. 7 times 10 to the 3rd, or 7 times 1,000 is 7,000. 4 times 100 is 400. 9 times 10 is 90. 3 times 1 is 3. That gets us the value of each place for the numbers. And to get the total value to understand what's going on, we would add all of those together. So that's another way of representing what we saw in the previous slide. And this is very useful representation because we can just take that and borrow it into the representation and understanding of binary numbers. So let's take a binary number here. The number is 10110. So this is in binary. How do we figure out its value in decimal? So we have in each, again, a number of numbers, each with its position, and each of those positions has a value. And in binary, since it uses 2 digits instead of 10 digits for each position, we're going to do the exponents on 2. So the first position is 2 to the 0, 1, 2 to the first, which is 2, 2 to the second, 2 to the third, 2 to the fourth, and so on and so forth. So the first position is 1s, the second one, 2 to the first, is 2, that's 2s. The third one, 2 to the second, is 4, so that's the fourth position. 2 to the third is 8, 2 to the fourth is 16s. So again, we can do our calculation the same way that we actually use the decimal system. 0 times 2 to the first, 2 to the 0 is 0. 1 times 2 to the first is 2. 1 times 2 to the second is 4. 0 times 2 to the third is 0. 1 times 2 to the fourth is 16. We can add 2 plus 4 plus 16. And the value of, or the decimal representation of the binary number 10110 is 22. So 10110 is the same as 22 if represented in the decimal system. So it's actually, if we understand that both systems are using the same kind of background math behind the scenes, the same sort of calculations, even though we're more used to one than the other, then it makes it very easy to switch between one to the other, to convert from binary to decimal and decimal to binary. So let's walk through the steps of converting from binary to decimal. The first step is to draw a conversion box, something like we just saw. And this is a conversion box for binary numbers. So we have our places and what each one is worth, starting from 2 to the 0 all the way up, in this case, to 2 to the 7th. So there's 8 places. And underneath, I've represented the value of the second row in simple decimal so that we can remember and do the math easily. So that's the first step. You just draw a conversion box like this. Then enter the binary number that you want to convert to the decimal and enter that in the top row. So here we have 100011101. Now we can do our multiplication. The first one is 1 times 1, or 1 times 2 to the 0. 1 times 1 is 1. 0 times 2 is 0. 1 times 4 is 4. 1 times 8 is 8. 0 times 16 is 0. 0 times 32 is 0. 0 times 64 is 0. And 1 times 128 is 128. So we have the value of each position in this number. The next step is then to add them together, which we can do down here. 128 plus 8 plus 4 plus 1 is 141. So we've just converted the binary number 10001101 to decimals, and the decimal representation of that same number is 141. So take a moment and do this exercise. I've copied the steps that we just went through for converting from binary to decimal there in the bottom right-hand corner. Take a moment to enter, calculate, what are the decimal equivalents of these numbers? 101, 111, 1 with 5 zeros, 10101, 00101010, and 1 followed by 7 zeros. And note that in binary numbers, we often break up larger blocks into blocks of 4 digits for the sake of readability. And in this particular case right here, you notice that for the sake of readability, we've added zeros at the beginning. But actually, as you may note, this number and this number, well, I won't tell you. You can figure it out. All right, take a moment and do the calculation. Okay, so here's the answers. The decimal equivalent of 101, if we do the multiplication, we're going to come up with a 1 in the 4's position, a 0 in the 2's position, and a 1 in the 1's position, which give us 4 plus 0 plus 1. 101 is 5 in decimal. Here we have the 1's position, the 2's position, the 4's position, and the 8's position. Each one has 1 in them. So we have 8 plus 4 plus 2 plus 1. So 1111 in binary is 15 in decimal. When we have 1 0 followed by, 1 1 followed by 5 zeros, that 6th position there is the 32nd place. So 32nd plus 5 zeros is, 32 plus 5 zeros is 32. Here again, we have 6 positions. We have 1 0 1 0 1 0. So 1 in the 32nd place, 1 in the 8th place, and 1 in the 2's place. 32 plus 8 plus 2 is 42. This number and this number are exactly the same. The beginning zeros there are just to make it readable. But this is in the same 32nd place. So this is the same as this. They're both 42. This last one, if we count here, we have the 2's position, the 4's position, the 8's position, the 16th position, the 32 position, the 64 position. Oh, I missed one. Anyway, let's do that again. 1, 2, I think that's what I got wrong. 1, 2, 4, 8, 16, 32, 64, and 1. Or, with 8 positions, we know that this position is 2 to the 8th, which is 128. And so 1 followed by 7 zeros is 128. All right, that was binary to decimal. We can do the same thing doing decimal to binary. So let's walk through those steps. Very similar. We can actually use the same conversion box. So first of all, we can draw the same conversion box. What we do in this case is we take the decimal number that we have and we compare it to the highest binary value in our conversion box. Then we see if the binary value in that box is smaller than or equal to the decimal number that we're looking at. We'll put a 1 in that position. Then we'll subtract the value in that position from the decimal number that we're trying to convert. Let's see how this works. repeating this in each position, of course. So let's convert 163 to binary. So 163 is in decimal. Let's convert that to binary. We're going to take 163 and we're going to compare it to the value in the first, or the highest here that we have binary box is 128. 163 is greater than or equal to 128. So the binary value is smaller than the decimal value. So we're going to put a 1 in this position, and then we're going to take 163 and subtract it from that value. 163 minus 128 is 35. We're going to repeat this. So now we're working with 35. We're going to go to the next position. In this case, the binary value is not smaller than or equal to the decimal number. So we're going to put a 0 there. Then we go to the next position. In this case, 32 is our binary value. It is smaller than 35, so we're going to put a 1 in that position. Oh, jumped ahead a little there. We'll put a 1 in the position, and then we'll subtract 32 from 35, which gives us 3. And then, of course, we can easily see that these are all going to be zeros because all of these binary numbers are larger than 3. So we can jump down here, see that finally we have a value that is smaller than or equal to 3. So we can put a 1 here and do our subtraction again. 3 minus 2 is 1. We'll put the 1 position there. We're now working with 1. Again, this position, 1 is smaller than or equal to 1. So we're going to put a 1 there, subtract 1 minus 1, which gives us 0. And we're done. So now we've taken this decimal number, 163, and we can see that in binary, 163 would be represented as 101,00011. Okay, take a moment to do that same calculation. Again, I've given you the steps in the lower right-hand corner there to remind you. Take a moment to give the binary equivalents of 9, 27, 68, 216, and 255. Okay, let's walk through the answers of our conversion from decimal to binary. So the binary equivalent of 9 is 1001. So this is our 8th position. That's the highest one that is smaller than or equal to the decimal value. 9 minus 8 is 1. So we put a 1 in the 8th position, a 0 in the 4th position, a 0 in the 2th position. 1 is smaller than or equal to 1. So we put a 1 in the 1's position. 1 minus 1 is 0, and we're done. 9 is 1001 in binary. "27 in binary is this. And note that I've put this number in the readable 4-digit blocks. This is actually our first digit. And this is the 32nd position. So the next one will be 64. 32nd is the first one that is smaller than, sorry, we're working with 27. This is the 16th position. This is the 32nd position. 16 is the first binary value that is smaller than or equal to 27. So we put a 1 in that position, then subtract 27 from 16, sorry, 16 from 27, which is 11. Our next one in the binary position is 8. 11 minus 8 is 3. So in the 4th position, we have a 0. In the 2's position, we have a 1. 3 minus 2 is 1, so a 1 in the 1's position. And this is 27 in binary. 68, again in the 4 block, we see that we will start here with a 1 in the 64th position. 68 minus 64 is 4. So we're going to have a 0 in the 32nd position, a 0 in the 16th position, a 0 in the 8th position, a 1 in the 4th position, And then 4 is what we have left over, and 4 minus 4 is 0, so all the rest are zeros. Next, 216. Well, 128 times 2 is 256. So the next highest here in the 9th column would be 256. So we have to start here at 128, which is the first number that's smaller or equal to 216. 216 minus 128 is 88. So we're going to go and put a 1 in the 64 position. And then subtract 64 from 88, which gives us 24. So the 32nd position will have a 0, and the 16th position will have a 1. 24 minus 16 is 8, so there's a 1 in the 8 positions, and the rest are zeros. And lastly, 255 in binary is 8 ones. So the 9th one would be 256. That's 1 too many, so we start with the 128 position. And if you do the math, you can see that we'll have to have a 1 in every single position all the way down. And so if you see 8 ones, that's 255 in binary. So here's some sanity checking rules for conversions. Remember that binary can only be 1 or 0. So if you've got any other number going there in your binary number, it's not right. Another thing to remember as you're going from decimal or from decimal to binary, or trying to figure out the value in decimal of a binary number, is that odd numbers will always have a 1 in the ones column. Think about that. Odd numbers in binary will always have a 1 in the ones column. So if you see a 1 in the ones column, it's going to be an odd number, right? Because you're going to end up subtracting 2 or 4 or 8. And if you get down to 2 and it's an even number, you're going to end up with 2. 2 minus 2 is 0. But if it's an odd number, you'll have 1 left over, and you have that 1 in the ones column. All right, so odd numbers always have a 1 in the ones column. Right? We just thought that through. So you can also think about, why is that true for even numbers? Where is it going to stop and reach 0 when we do the subtraction? Always in the 2's column, right? Right. And then lastly, each column's value is the sum of all of the previous columns to the right, plus 1. So think about that. In decimal, what columns comes after 999? Once we add 1 to that, so once we add up the maximum of that column's value, we're going to switch to the next column, which is 1,000. So that's 999 plus 1. The same thing. If you add up all the values of the binary, so the first column is 1. Once you get to 1, you have to switch over and do the next column. So 1, 0 in binary is 1 plus 1, 2. 1, 0 in binary is 2. And here you have to really remember what the value of the columns are. So you go back to those exponents, 2 to 0, 2 to 1, 2 to 2, etc.